we will begin the discussion on isolated converters. Till now, we have been discussing on non-isolated converters, mainly the buck converter, the boost converter, and the buck boost converter, which are called as the three primary converters. We will use the buck converter and the buck boost converter and derive the isolated versions of these. Isolation has many benefits. Firstly, there is no physical connection between the primary side and the secondary side of the galvanic isolation. The primary side, which is the input source side, and the secondary side, which is the load side, if it is isolated, there will not be any surges passing on to the load side and damaging components on the load side. There will be reduced conducted emission both ways, from the source side to the load side and from the load side to the source side. Not only that, the galvanic isolation gives us one more degree of freedom by means of the turns ratio. By using turns ratio, I can use the buck derived forward converter or the other versions of the converters to also provide you a boost. The output voltage can be higher than the input voltage because of the turns ratio freedom. And you can have multiple outputs. That is, you can have the same converter, 5 volts, plus minus 15 volts, and so on. So these are the advantages that you gain by putting in a transformer. And most of the practical power supplies will use the transformer or the isolated version of the converter for most of the practical power electronic equipments. We shall now try to look at and study some of the isolated converters. Firstly, we will begin with buck derived isolated converters. There are many buck derived isolated converters. We will be studying the following. One is the forward converter, issues involved with that, and then we have the push-pull version or the push-pull converter, then the half bridge converter, followed by the full bridge converter. These four are the important converters which are very popular in most power electronic equipments, and we will discuss these. Then on the buck boost derived isolated converters, there is one very important converter which is one of the most popular converters in use, and that is the flyback converter. So we will discuss this flyback converter also. Let us now see how the forward converter circuit topology is. This forward converter is a buck derived isolated converter. So we shall start from the buck converter topology. So let us have this unregulated source Vi, and we know the buck topology. You have the BJT, you have this diode, the inductor, capacitance, and the load. So this is the buck converter circuit. You have Vi, R0, V0, L, and C. Now let me do one thing first. Let me shift this transistor which is on the top rail to the ground rail, because then we need to drive this transistor with respect to the emitter. A lifted up floating emitter is much more difficult to drive than a grounded emitter. So let me make some space here and let me place the BJT here. Now the emitter is on the ground side, same direction of the current flow. You see that the current flows in the same direction. So only it is on the return rail. Now this emitter is grounded. If I take this is ground, and driving this BJT or MOSFET with respect to the ground is much easier. So normally we will do that. So we'll put the BJT or the transistor that is the control switch on the return rail rather than on the top rail. Now we can remove this transistor. So we will remove that and close that. Another modification that we will do in the representation is, let us put label symbols for the ground. This is the ground. I'll put a label symbol for the VCC or VI, the positive of the source. Now I can remove this without loss of generality so that it doesn't clutter up the circuit. Now that we have removed this still represents the same buck converter circuit. I will now put this switch down vertical like this, in this fashion. So this is still the same buck converter circuit, and I will shorten this. Let me put the label here and remove this portion. So this becomes the buck converter circuit, still the same buck converter circuit, only with some repositioned switch positions. Next, I would like to insert the isolation. So at that point, let me put in the primary winding, then I will put the secondary winding and join them up. It is still not complete. I can't just join them up here, because let us say when the inductor is freewheeling. When the inductor is freewheeling, this diode is conducting and it is effectively shorting the secondary. When it shorts the secondary, the primary will draw a huge current and blow up this transistor. Therefore, we cannot allow shorting of the secondary when the inductor is freewheeling through this diode. So we will put a diode here so that you don't have a reverse current flow. I will make some space and put the diode. So at least now it is safe. Even if this is freewheeling, the voltage, this diode will not allow short circuit to happen across the secondary and thereby reflect it onto the primary. Next, let me mark this VP, Vs, and this is turns ratio 1:1. This voltage here, let me call it as VA. This is the inductor current IL, this is output I0 current, and this is IC. This portion from VA onwards is nothing but pure buck converter. So observe here that the circuit is still incomplete. Let us see what happens. Now let us say this transistor is on. The moment the transistor is on, there is going to be a magnetizing current that is going to flow here, and the reflected load current also will flow through here. When you switch it off, inductor will freewheel. There is a reversal of polarity. The dot will become negative, non-dot end will be positive, dot will be negative, non-dot end will be positive. This diode will be reverse biased. Because this diode is conducting, what will come across that will be a negative voltage. This diode will be reverse biased and off. So there is no path for the internal flux of this core to reset. Meaning when there is a current flow here, you have switched it off, there is a L di by dt, the voltage across this, di by dt has been cut off. There will be a huge voltage because of the negative di by dt, and a huge voltage will appear across this and blow up this transistor. Therefore, you have to provide a path for the flux in the core to reset. So we will see that there is a path for the inductor current to flow in this direction here. So we will make a path in this fashion. We will put a resistance and the diode like this. So we will call this as RM and DM. Diode corresponding to the magnetizing flux reset path, Rm is corresponding to the magnetizing current reset path. So now when you switch this on, there is a current flow through this magnetizing current and the load reflected current flowing through this, and when you switch off, there is no load reflected component, only the magnetizing portion of the current will freewheel like this. It will freewheel and decay with Lm by Rm time constant. Lm is the mutual inductance and the Rm is this resistance. So L by R time constant, it will start decaying and go to 0, and once the magnetizing current goes to 0, the flux in the core is reset and brought back to its original state, so that you may you can start the next cycle by switching this on. Now this is the complete forward converter circuit, a working forward converter circuit. Let us now try to understand this forward converter circuit. Let us try to understand its operation and the waveforms at various points. Now if you see this portion of the circuit, the one that I am indicating with the cursor, this portion of the circuit on the secondary side is exactly like a typical buck converter. So you have two switches here, two diodes. If you consider this as throw 1 and throw 2, and this is the pole voltage, VA would be the pole voltage, have the inductor current, capacitor current, I0. All this portion of the circuit, the waveforms will be very typical like the buck converter circuit that we discussed. On the primary side is nothing but a chopper or a switcher, and we will discuss the waveforms of the chopper and the switcher, and also this portion of the circuit where you are doing core resetting. These are the extra portions that will come apart from the regular buck converter waveforms. Now let us relate the regular buck converter waveforms to the forward converter. Let us look at the buck converter waveforms for now and revisit this buck converter along with the waveforms here, so that we again remember these waveforms. This portion, the buck converter portion, very much similar to the secondary portion of the forward converter. All these waveforms are valid, only we will have to look at the notations and change the notations to the forward converter notations. So now what I will do is copy these waveforms which we had drawn for the buck converter and place it along with the forward converter, and in comparison change the values and the notations. So let us place the waveforms, move it. So here you see that these are the same buck converter waveforms. During DTS time, we have the switch on, 1 minus DTS time, switch is off, 2 cycles. So again DTS and 1 minus DTS. Now VP, the pole voltage, will map to VA. So let us change that. So I will remove that and put it as VA. So VA here, and when during DTS, the voltage here, what will happen when the switch is on, what will appear is VI, and this VI, look at the dots, will translate to the secondary voltage as N times VI. The N times VI will appear across at VA. So therefore this VI will change to N times VI. So let us make that change, N times VI, and then during the time when this is off, the inductor will freewheel through this diode, and the potential of VA with respect to here the output ground would be 0 and 0. So this will be the VA waveform, and from the VA waveform, all these waveforms are typical buck converter waveforms. For example, the voltage across the inductor VL will remain unchanged, except that here VI minus V0 will become NVI minus V0. So let us make that small change. So this will become NVI minus V0, NVI minus V0. This will remain V0 when the inductor is freewheeling, this potential is 0, VA potential is 0, and the other side of the inductor is at minus V naught. So that is what we have indicated here, remains unchanged. Now let us take the inductor current IL. The inductor current IL also will be similar. You see the inductor current rises. Now it rises for a change of delta IL. In dTs time, it will be N Vi minus V naught by L. So instead of Vi minus V naught by L, it will become N Vi minus V naught by L. Let us make that change. So we have N Vi minus V naught by L. On the falling side, during the freewheeling time, the voltage across the inductor is minus V naught. So this will remain minus V naught by L. Look at the IC current waveform. IC, there is no change. It will be this ripple component of the inductor current only that will flow through IC. Zero average current because amp second balance has to be maintained. The average value of the inductor current is I naught. That still remains I naught. Now let us mark some symbols here. Q for this BJT, and the current that flows through Q is IQ. And let me mark this as D1 diode. This is D2. This is ID1 and this is ID2. So these are the currents that I have marked. So now let us look at some of these waveforms. Now look at the waveform here IT1P. IT1P for the buck converter was the BJT, the controlled switch current. So when during DTS time, when the control switch was on, this was the current that was, this part of the inductor current was flowing through that switch. So you still have the inductor current flowing here. So what will flow through ID1 will be equivalent to IT1P. So let us change this IT1P to ID1. So it will be that current that is flowing. So ID1, this diode D1 will be on whenever Q1 is on, and only that part of the inductor current will flow through it during DTS time period. Now, if you look at this waveform IT2P, it should be same as ID2. So I can just change it to ID2. Nothing else will change in these two waveforms. So now what is the current IQ through this primary side switch? So when the switch is on, the current flow through the primary side switch IQ and I primary are same, and I primary is the reflected current. Whatever ID1, N times ID1 gets reflected onto the primary, and IQ is the same as that. So IQ is equal to N times ID1. We can say that. So therefore, if I change this to N times ID1, it becomes IQ current. So if I say N times ID1, all the values here will be multiplied by scaling factor N. So let's say this becomes N, and the average value will be N times I naught. So this wave shape is the wave shape that you can expect to see through the BJTQ or IQ. With respect to the primary side switches, with respect to VT1P, the voltage of the VT1P, I will discuss that separately. VPT2 is the voltage across the diode D2. There is no change except that Vi becomes NVI. So I will remove the voltage portions of the waveform now, and I will get back to that. In the meantime, before that, I would like to give the input-output relationship. So let us write down the input-output relationship, and for that we need to look at the inductance voltage waveform, that is the voltage waveform across the inductor. We know that we have to look at the volt-second balance. So what is the voltage during dTs period multiplied by the time period will give the area of this rectangle, and during the 1 minus dTs period we have minus V0 and multiplied by 1 minus dTs will give the area of this rectangle. These two should be equal for volt second balance, and that will give us the input output voltage relationship. So let us now write down the input output voltage relationship and see what is the change. So here we are having NVI minus V0 into dTs plus minus V0 into 1 minus dTs is equal to 0. So let me cancel out these, and the remaining variables, if I rearrange them, V0 is equal to N Vi into D. So this is the input output relationship for the forward converter. Look here that there is a new term here, N. N is the turns ratio of the transformer that comes in and gives in an additional degree of freedom. So the designer has a flexibility in the choice of N, and therefore the output can even be higher than the input. So in a typical buck converter, the output is always, V0 is always less than Vi. But here, even though D varies from 0 to 1, 0 to is less than 1, in this case, the duty cycle cannot go more than 50%, because if the transistor is on for 50%, there needs to be an equivalent amount of time needed to give for the core to reset. So therefore, normally the duty cycle we keep it at 50% and use the freedom of N to scale it to any level. So if you have N is equal to 10, you can have V0 much greater than Vi. So therefore, buck and boost, everything is possible because of the isolation, because of the scaling provided by the isolation. However, this N is a fixed, a variable which cannot be changed dynamically. D is a variable which can be changed dynamically. So this can be taken care at the end, at the design time once, and D can be used as a control input to take care of changes in a dynamic fashion. So D becomes a control input. So this is the input output relationship for the voltage. In a similar manner, in the same manner, we can also get the input output current relationship. We can use the power balance, saying Pi is equal to P0, which means Vi II average, because the input current is switched, and therefore the average of that will be Vi into II average will be equal to P0, which is V0 into I0. So now we can replace this V0 with the input output relationship that we have just derived, and that means that we can say equal to N Vi into D into I0. This will be the P0 output power. So this implies that II average will be equal to N I0 into D. So this will be the input output current relationship. So this value is the average of this IQ. Average of this IQ waveform will be this in terms of N, I0 and D.